So Huckel molecular orbital theory, I have written shortly as Huckel Hmot. Even it is abbreviated as Hmot, Huckel molecular orbital theory. Okay, listen, this theory is applicable, right? Huckel molecular orbital theory is applicable to conjugated systems, conjugated polyene systems. Okay, it is applicable to conjugated polyenes. Okay, so very specifically, system containing pi electrons. Okay, now, and here there are certain important approximation that Huckel has made. Right, the approximations are: number one, listen, since this theory is applicable only to pi electrons, you need not worry about sigma electrons at all. So sigma electrons do not interact, okay, with the pi electrons. So sigma and pi electrons, sigma and pi electrons do not interact. Okay, so sigma electrons, okay, are simply neglected. So sigma electrons are neglected. Only pi electrons are considered in Huckel Hmot. Okay. Then second important point is that in Huckel molecular orbital treatment, we need not worry about whether the system is cis or trans, right? Whether it is cis alkene or trans alkene, right? You need not worry about that. Okay. Huckel theory, just to see how many conjugated pi electrons, pi bonds are there, okay, and what is the pi electronic energy. It does not consider whether the polyene system is cis or trans. Okay, cis and trans geometries are not considered, considered. Okay, you should just treat as a alkene, that's all. Okay, then how molecular orbitals are formed? Listen, since it is a Hmot molecular orbital theory, you know very well atomic orbitals combine and form molecular orbitals. Which are all the atomic orbitals combined? Listen carefully. In each carbon, we see in this Huckel theory, we assume that the entire molecule is in the XY plane. So, molecule is assumed to be in XY plane. Okay. Since it is a conjugated system, the molecule should be planar, right? And the plane of the molecule is assumed to be exist in XY plane. Therefore, each carbon atom has a pz orbital which is perpendicular to the plane. See, each carbon atom, okay, let me draw like this. Each carbon atom has a p orbital, that p orbital is perpendicular to the plane. Okay, so this pz orbital, very specifically in carbon, is actually 2pz orbital. The 2pz orbital of one carbon and the 2pz orbital of the adjacent carbon, they interact. Okay, this interaction will form what is called the tri-molecular orbitals. I repeat, see, this is one pz orbital of one carbon. Suppose if we have another pz orbital on the adjacent carbon, right? This is also 2pz orbital. This 2pz and this 2pz, they combine and form what is called molecular orbitals. So we are going to use the same idea. Atomic orbitals combine to give molecular orbitals, MOs. Okay, molecular orbitals. And which atomic orbital we are going to combine? It is the 2pz atomic orbital of carbon. 2pz atomic orbitals of carbon combine to give pi molecular orbitals. We will get pi bonding as well as pi anti-bonding molecular orbitals. Okay, take note. Huckel, he made some approximations called Huckel's approximation. Huckel's approximations. What are they? Apart from the one we discussed before, he gave he made some approximation on the integrals that comes out from the variation theorem. Okay, using variation theorem, we'll find out the average energies of the pi molecular orbitals. Okay, using in those procedure, there are some integrals involving, and he gave some values for those integrals. Okay, and he gave some symbols for those integrals, and he calculated using those values. He calculated the pi electronic energy and resonance energy. Okay, etc. etc. Right. So we are going to discuss everything right as we go along. Let me introduce you. What are the integrals? He made it into some approximate value. Listen. The first integral is called Coulomb integral. C-O-U-L-O-M-B. Coulomb integral. Coulomb integral, which is generally represented as HII. What is Coulomb integral? See, very simple. HII is nothing but integral of I represent ith carbon atom. I represent ith carbon atom. So it is the wave function of 2pz orbital, right, of ith carbon, Hamiltonian operator, into wave function of 2pz orbital of ith carbon into d tau. This integral is shortly represented as HII. Listen, hereafter we need not write every time as pi 2pz and all. We will simply write phi. Here phi means 2pz orbital. Okay, this phi represents 2pz orbital. Phi means 2pz orbital on ith carbon. Okay, H operator, phi, d tau. This integral is what we call as Coulomb integral. And Huckel gave a symbol for the integral, okay, which is nothing but alpha. Right? What is actually alpha? Very simple. Listen, suppose if a carbon atom has a 2pz orbital, and if that orbital contains one electron, if one electron is present in 2pz orbital of carbon, then the energy of that electron is nothing but alpha. Right? Alpha is nothing but Coulomb integral, which gives the energy of an electron present in 2pz orbital of carbon. Okay, take good. Next integral is called resonance integral. Resonance integral. What is that? It is represented as Hij. Hij. Let me write that integral here. Hij. What is Hij? It is the integral of 2pz atomic orbital on ith carbon, then Hamiltonian operator, then 2pz orbital of jth carbon into d tau. You can also put complex conjugate, nothing wrong with it. Right? Phi star, H operator, phi j, d tau. This will give you a value called a resonance integral. Listen, according to Huckel theory, if the ith carbon and jth carbon, if they are adjacent, if they are directly bonded, see, if suppose this is the ith carbon and this is the jth carbon, if I and j are directly bonded, then this integral value is taken as beta. Okay, resonance integral is taken as beta if ith carbon and jth carbon, I and j are directly bonded carbon atoms. Suppose if ith carbon and jth carbon are not directly bonded, say for example, I have some ith carbon here and jth carbon is just away from the ith carbon. It is not adjacent, you can say another way. If the jth carbon is not adjacent, then the resonance integral, right, becomes 0. Okay, resonance integral becomes 0. This is the second important approximation called Huckel's approximation. Okay, take note. So when we should give 0, if I and j are not directly bonded. Okay, then we should give the value as 0. Now, let me move on to the next approximation called the overlap integral. Let me write here. We have two more integrals. Next one. So I have written Coulomb integral, resonance integral. Then third one, let me write normalization first. Normalization integral. Normalization integral, which we represent as SII. Normalization integral is generally represented as SII. What is SII? Listen. SII is nothing but integral phi star into phi into delta. Since the 2pz orbital, atomic orbital wave functions are normalized wave function, so integral phi star phi delta should be equal to 1. So normalization integrals are always given the value as 1. This is very, very true, because we know very well, if the wave function is normalized wave function, then integral phi star phi delta should be equal to 1. This is correct. Then he made one more approximation. This is very, very important, called overlap integral. Overlap integral, which is denoted by the symbol Sij. Sij is called overlap integral. What is overlap integral? Sij is nothing but integral phi star. Okay, this is the wave function of ith carbon. 2pz atomic orbital of ith carbon, and this is 2pz atomic orbital of jth carbon into d tau. Listen, do the atomic orbital overlap or not? Listen, Huckel took this value as 0. He assumed that there is no overlap between 2pz atomic orbital as adjacent carbon. Okay, he assumed this as 0. But actually speaking, some overlap should be there between the 2pz orbitals on adjacent carbon, but Huckel assumed the value as 0. Okay, take it. So first we'll discuss application of this Huckel theory on ethene system. It's a very simple system, ethene. Ethene has one carbon-carbon double bond. Ethene molecule has one carbon-carbon double bond, so there are 2 pi electrons. So how many pi electrons are there? Pi electron. Since there is one pi bond, you know very well, if you have a multiple bond, one bond should be sigma, the remaining bond should be pi, correct? So in double bond, one bond is sigma, the other bond is pi bond. And each pi bond contains 2 electrons, so number of pi electrons, right, in ethene is 2. Okay, so what is the molecular framework? And what is the number of electrons present? Okay, then each carbon atom has a 2pz orbital, right? Don't worry about the hydrogen atom and other thing. I am going to focus only on the 2pz orbital. See, in ethene, each carbon atom has a 2pz atomic orbital. Let me write here. So this is 1 2pz. Let me take this as carbon 1 and this is carbon 2. So we have a 2pz orbital on carbon 1. And another 2pz orbital is present in carbon 2. Okay, and each orbital has 1 electron. So now we have 2 pz orbital on adjacent carbon. Okay, these 2 p orbital combine and form molecular orbitals. Okay, so how to combine? So I am not going to discuss the complete procedure, but I will give you the essential ideas. The idea is this: you should form a determinant called Slater determinant. We should form a determinant called Slater determinant. Slater determinant. What is that? Listen, you just see how many p orbitals, right, are involving in the conjugation. So in ethene, we have only 2 p orbitals. So I am going to consider only the 2. Right? So it involves this determinant involves some elements What are they? Listen. H111 minus E into S11. I am writing the first row, H11 minus E into S11, where E is the energy. The next one, H12 minus E into S12. Then second row, H21 minus E into S21. Then H22 minus E into S22. So we should write a determinant, okay, whose rank or order, right? Order of the determinant is 2. So because it has 2 rows and 2 columns. Why? There are 2p orbitals involving. Therefore, there should be 2 rows and 2 columns must present in the determinant. Okay. Now we will apply the Huckel's approximation. What is the Huckel approximation? See here. H11, I have told you H11 is called Coulomb integral. H22 is also called Coulomb integral. Coulomb integrals are taken as alpha. Coulomb integrals are taken as alpha. Okay. Then what is this H12? H12 is the overlap between 2pz of carbon 1 and 2pz orbital of carbon 2. H12 and H21, they are overlap integrals, they are resonance integral. Yeah, they are resonance integral. Since carbon 1 and carbon 2 are adjacent, they are directly bonded. See, in this case, C1, C2 are directly bonded. H12, H21 values equal to beta. If they are not directly bonded, 0. Since they are directly bonded, the value is beta. Then what about this S11 and S22? S11, S22 are called normalization integral, and normalization integrals are always taken as 1. Then overlap integral S12, S21 are called overlap integral, and I told you Huckel assumed the overlap integral value as 0. Okay, take that. Now I will substitute the Huckel approximated values in the determinant. So in the place of H11 I will put alpha minus E into S11 value is 1, so you will get E. Alpha minus E. This is H11 minus E into S11 value is 1, so 1 into E. Okay. Then H12 is 0 minus E S12. H12 is beta, no? Right. H12 is beta minus E into S12. S12 is overlap integral, is 0. Therefore, E into 0 becomes 0. So leave it. Then second row again, see 21, H21 which is beta minus E into S21 is 0, so that becomes 0. Then the fourth element H22 is alpha minus E into S22 is 1, so we will get alpha minus E equal to 0. Right, take this. How to simplify this? Now I am going to divide first row by beta and second row also by beta. If I divide by beta, similarly, we have to divide beta here also, but 0 by beta is 0 only, so need not worry. So I am going to divide first row and second row by beta. So what we get is alpha minus E by beta. Here beta by beta is 1. Here also beta by beta is 1. And here we get alpha minus E by beta equal to 0. Okay. Now let me take this value as x. So put alpha minus E by beta equal to x. So this becomes x now. X 1 and this also x equal to 0. Now you know we will have to simplify the determinant. So first cross multiply these two, you will get x square. Here you will get x square. Then you have to cross multiply this. 1 into 1 is 1, but while doing cross multiplication of this diagonal, you should put minus. Minus 1 equal to 0. Okay. Then x square equal to, bring the minus 1 to the other side, you get plus 1. or x is equal to plus or minus 1. So there are two possible values of x. Yes, we should get two possible values because the two atomic orbital combine to form two molecular orbitals. Okay, listen, the two atomic orbitals combine. See here, we have two atomic orbitals. These two atomic orbitals combine and form two molecular orbitals. Okay, are you able to follow?
Yes.
So I'll put these x values here and we'll find out the energy. Okay, listen, if first I'll put x is equal to plus 1 and x is equal to minus 1 in this formula. If you put x is equal to plus 1 here, what we get? See, alpha minus e by beta equal to plus 1. Then multiply this here. So alpha minus e equal to beta. Bring minus e this side and plus beta this side. So what we get is e is equal to alpha minus beta. This is one energy value. Here, if I put x is equal to minus 1, we get alpha minus beta equal to minus 1 or alpha minus e equal to minus beta. Right? Bring this minus beta this side and minus e that side. So we'll get e is equal to alpha plus beta. We get two energy values. Okay, take a look. Listen, here alpha and beta values right, are always negative. Both alpha and beta values are negative. Since both alpha and beta values are negative, alpha plus beta will give lower energy and alpha minus beta will give higher energy. Therefore, I'll put this as E1 and this as E2. This is lower energy level and this is the higher energy level. So, we get two molecular orbitals. Okay, just copy down. I'll write in the next page. We get two energy values. Why? Because the two atomic orbitals combine and form two molecular orbitals. Okay, so this is energy. Energy is increasing in this way. The lower energy molecular orbital, whose energy is represented as E1. E1 is nothing but alpha plus beta. And the higher molecular orbital, higher energy molecular orbital is represented as E2. The energy is represented as E2, which is given as alpha minus beta. This is called pi bonding molecular orbital and this is called pi anti-bonding molecular orbital, pi star. Okay, so this is the energy diagram of pi electrons or pi molecular orbital diagram, of ethene. Ethene has two pi electron, I told you. Listen, each molecular orbital, listen carefully, each molecular orbital can accommodate two electrons, like atomic orbital. Okay, therefore, this molecular orbital accommodates two electrons. This is called the ground state. So, what is the ground state configuration? Ground state configuration is very simple. Pi molecular orbital has two electrons and pi star molecular orbital has no electron. Okay, this is the electronic configuration of ground state configuration of ethene. Okay, and this is called pi electronic configuration. Remember, the ground state configuration is the pi electronic configuration of ethene. Okay, take. Yeah, see each electron
2 alpha plus
beta. Very good. That is called the pi electronic energy. So, what is the pi electronic energy? Pi electronic energy, right? Pi electronic energy. We represent pi electronic energy by the symbol E pi. What is E pi for ethene? Since both the electrons are present in a lower energy molecular orbital whose energy is E1, so it should be 2 into E1 or 2 into E1 value is alpha plus beta. So the energy of the pi electronic energy of ethene is 2 alpha plus 2 beta. Ethene has two carbon atoms, is it? And each carbon atom had one 2pz orbital. So this carbon has one 2pz orbital with one electron and this carbon has one 2pz orbital with one electron. Suppose if the two p orbitals do not combine, what will be the total energies of the electrons? Listen, if there is no bonding, then the energy of this electron, which is present in 2pz orbital of carbon, is nothing but alpha. Similarly, this electron is also present in 2pz orbital of carbon and the energy is alpha. So, if there is no bonding, then the total energy of the electron is alpha plus alpha, 2 alpha. Okay, now what is actually the pi bonding energy? Let me write here. Pi bonding energy. Pi bonding energy is nothing but pi electronic energy minus, okay, what is the energy before bonding? Before combining the atomic orbital, which is 2 alpha. So pi electronic energy is 2 alpha plus 2 beta. This is 2 alpha. So 2 alpha cancel. We get the values 2 beta. We get the values 2 beta. I have told you already, beta is always negative. So negative into 2, so you will get some negative value, which means because of this bonding, this much amount of energy is lowered, decreased. I can say that way. Listen, if there is no bonding, energy is 2 alpha. Because of bonding, okay, it's called pi bonding energy. Pi bonding energy comes out as 2 beta, which means this much amount of energy is reduced in the system. So system gets stabilized. That is the reason why pi bonds are formed. Okay, Huckel theory provides explanation, right, for the reason for the formation of pi bonding in systems. Okay, suppose, let me ask a question. Suppose the ethene is present in some excited state. Okay, so I'll consider some excited state of ethene. Okay, in some excited state, ethene has this configuration. See, pi molecular orbital, pi bonding has 1 electron and pi anti-bonding has 1 electron. Okay, then find the pi electronic energy, right, in that state. See, what is the pi electronic energy? How to calculate? You know very well. In ethene, see, we have 2 molecular orbital. This is pi bonding and this is pi anti-bonding. Now the given configuration is pi bonding has 1 electron and pi star anti-bonding has 1 electron. Okay, this is, I am keeping the multiplicity as such. Okay, now listen, pi bonding electron has now only 1 electron and pi anti-bonding has 1 electron. Therefore, what is the pi electronic energy? Pi electronic energy is, here we have 1 electron, so, and the energy of this level is E1 and the energy of this level is E2. So 1 into E1 plus 1 into E2. Okay, 1 into value of E1 is alpha plus beta, you know, plus 1 into value of E2 is alpha minus beta. So 1 into this alpha plus beta plus alpha minus beta. So plus beta minus beta cancel. We get the electronic energy as 2 alpha in this excited state. Okay, so in this excited state, see, this excited state is equivalent to what? See, we all well aware of the application of Huckel theory on ethene. Okay, in one of the CSR examination, they asked a question like this: calculate the pi electronic energy of 1 pentene. They have asked a question like this: 1 pentene using Huckel molecular orbital theory. Listen, the 1 pentene, 1 carbon 2, 3, 4, 5. This is pentane. 1 pentane means in first carbon you put a double bond. This is 1 pentene. Okay. Yes, tell me how many pi electrons are there?
2 pi electrons.
How many 2pz orbital combined to form molecular orbital?
Okay.
Only 2, correct? 2p. So this is exactly similar to
Ethene system.
Ethene molecules. This is similar to ethene. Why? We are not supposed to bother about the sigma bonds. According to Huckel approximation, you need not worry about sigma bonds. Okay, so the structure may contain even 100 carbon atoms. No, need not worry. If you have one double bond, you should treat this molecule as ethene. Therefore, what is the pi electronic energy of this compound according to Huckel theory?
2 alpha plus 2 beta.
2 alpha plus 2 beta.
Very good. That's all. 2 alpha plus 2 beta. Okay. Listen, yeah. The second question, let me write here. Okay. Listen. Compare the energy of these systems. Okay. Compare. This is system A. This is system B. This is system C. Compare the pi electronic energies of this system, okay, according to Huckel molecular orbital treatment. Compare the pi electronic energies of these systems. Yeah, listen, Huckel theory does not consider the trans and the cis structure and all. According to Huckel theory, all these systems contain one pi bond, that's all. So, pi electronic energies of all the systems are equal. So, pi electronic energy of A, pi electronic energy of system B, and pi electronic energy of system C all are equal. Okay, take. In ethene, we get two pi bond orbitals. Now, the question is, what are their wave functions? Wave functions of pi molecular orbitals of ethene. So, in ethene, we get two pi molecular orbital. One is called pi bonding, the other one is pi anti-bonding. What are their wave functions? Yes, we can find the wave function, but I am not going to do the complete steps and all, but I am going to give you the result. Listen, it's very easy actually. This molecular orbital and this molecular orbital are formed by the linear combination of two pz orbital. So, let me take, this is the wave function of one 2pz orbital present on carbon 1. This is another wave function of 2pz atomic orbital present on carbon 2. Listen carefully, what is Phi1 and Phi2? Phi1, Phi2 are their atomic orbital wave function. Atomic orbital wave functions of 2pz orbitals on carbon 1 and carbon 2. Okay, they are wave functions of atomic orbitals. And you know very well, atomic orbital combine and form molecular orbital. Okay, listen, only two atomic orbitals are combined. Therefore, I am going to multiply these atomic orbitals by some coefficient. Okay, since they have half probability, so I will multiply this by 1 by root 2 and I will multiply this also by 1 by root 2. If you take the square of the coefficient, square of 1 by root 2, right? Similarly, square of 1 by root 2, if I add these two, I will get the answer as 1 because the wave function should be normalized. So, the ground state wave function, let me write this ground state wave function is psi1 for the molecular orbital. So, molecular orbital wave function psi1 equal to 1 by root 2 phi1 plus 1 by root 2 phi2. This is called bonding molecular orbital. For anti-bonding molecular orbital, I write psi2 is equal to 1 by root 2 phi1 minus 1 by root 2 phi2. What does this minus signify? Let me explain. Listen. So, psi1 is the wave function of the bonding pi molecular orbital, which is given as, take 1 by root 2 as common, so we get 1 by root 2 into phi1 plus phi2. Okay. Now, how to depict this wave function? Listen, we have two carbon atoms, right? In each carbon atom, we have a 2pz orbital. Since there is a plus sign in between, okay, it means there is no node. There is no node, meaning, see this two, you know very well, a p orbital has two lobes and the two lobes have opposite sign of wave function. Suppose if the upper lobe has positive sign for wave function and the lower one has negative sign. And since there is no node, plus sign means no node. I am sorry, this is plus, this also plus. Okay, this is plus, this is also plus. So sign remains same. Therefore, there is no node. When there is no node, you should retain the sign as is. If this is plus minus, this should also be plus minus. Okay, so this is how the atomic orbital combine. When they combine, we get molecular orbital. This is for pi bonding. Okay, I am talking about pi bonding molecular orbital. For pi bonding or molecular orbital, the two atomic orbitals, okay, orient like this. When they combine, we get, listen, the upper lobes have same sign, so they combine and form a bigger upper lobe, and the lower lobes are same sign, so they combine and form a lobe like this. And this is the structure of pi bonding molecular orbital. This is the atomic orbital orientation, proper orientation of atomic orbital to form pi bond, pi bonding molecular orbital. And when they combine, you will get this. Okay. The second molecular orbital, that is pi star anti-bonding molecular orbital. The wave function for this molecular orbital is given as psi 2. What is psi 2? Which is nothing but 1 by root 2. I will take 1 by root 2 as common. We will get phi1 minus phi2. See, this wave function is plus. When we move to here, plus become minus. It means there is a node between the two carbon atoms. So, listen, see, we have two carbon atoms. This carbon has a pz orbital, and this carbon atom has a pz orbital. Okay, since this carbon has plus sign, listen, I will put plus to the upper lobe and minus to the lower lobe. When you come to the second atomic orbital, sign is changing. Therefore, there is a node between the two p orbitals. There is a node. When there is a node, then if the upper lobe of this carbon is plus, then the upper lobe of this should have minus. So this is plus. Okay. So this is how the orientation of atomic orbital exists before bonding. Okay. When they combine, do they combine? No. Why? Because they have opposite sign. They cannot combine. Therefore, what will happen? What will happen is that the two atomic orbital move like this. It move away like this. This is plus sign, minus sign. This is plus, this is minus. This is the pi star anti-bonding molecular orbital of ethene. Okay. The next system is second system. Listen, let me write like this. This is allyl cation, allyl radical, and allyl anion. Okay, allyl cation, allyl radical, allyl anion. Okay, we are going to apply Huckel theory for these three systems. Listen here. So here I have a pi bond. So this carbon has a 2pz orbital. This carbon has 2pz orbital. And you know very well the cation also has an empty 2pz orbital. Here the 2pz orbital has 1 electron. Whereas here the 2pz orbital has no electron. So it is empty. Whereas here we have 3 2pz orbital. Each one has 1 electron. Here this 2pz and this 2pz has 1 electron, whereas this corner 2pz has 2 electrons. It has a lone pair. Okay, now listen carefully how to do that. How to do this type of problem. Listen, now we have 3 p orbital. Okay, so let me draw like this. We have 3 carbon atoms and we have 3 p orbitals. Don't worry about whether they contain 1 electron or empty. Don't worry about that. We have 3 p orbitals. So this is p1. The wave function of this is p2 and this is p3. When 3 p orbital combine, we get 3 molecular orbitals. We get 3 molecular orbitals. Okay. What are the energies of these 3 molecular orbitals? Listen carefully. I'll take this as E1, this is E2, this is E3. Actually, we should write determinant containing 3 rows and 3 columns, and we need to solve that. I'm not going to do that, but I'm going to give you the final energy. Okay, just try to remember this. E1, the lowest energy molecular orbital, has energy alpha plus root 2 into beta. Alpha plus root 2 into beta. And the middle one has energy equal to alpha. And the upper one has energy alpha minus root 2 into beta. Okay, this is the energy diagram for allyl cation, allyl radical and allylic anionic system. Okay. Okay, now first I'll take allyl cation. See, in the case of allyl cation, how many pi electrons are there? How many pi electrons?
Two pi.
Yes, we have only one pi bond, and here there is no electron, so we have only two pi electrons. So if I fill up the 2 pi electrons in this molecular orbital, pi bonding molecular orbital, okay, wave function of this is psi1, wave function of this is psi2, wave function of this is psi3, and energy of this molecular orbital is E1, E2, E3, right? Energy increasing in this order from bottom to top, energy increasing. I have 2 electrons, so in the ground state configuration, we should place both electrons in the psi1 molecular orbital. Okay, and what is the energy of this orbital? Alpha plus root 2 into beta. Since both electrons are present here, so you have to multiply this by 2. So pi electronic energy of allyl cation, let me write shortly plus. You need not write allyl cation every time, just put plus, meaning allyl cation. So for allyl cation, pi electronic energy is multiply this by 2, because for each electron energy is E1. I have 2 electrons here, so 2 into E1, so we get 2 into alpha plus 2 root 2 beta. So this is the pi electronic energy of allyl cation. So what is that? Pi bonding energy. I'll write shortly BE, meaning pi bonding energy. What is pi bonding energy? Pi electronic energy of allyl cation minus, observe carefully, here, see this carbon 2pz orbital has 1 electron, because I have a pi bond here. This carbon 2pz has 1 electron, this carbon has 1 electron. So let me draw here. Listen, suppose if the p orbitals do not involve in bonding, then this carbon has 1 electron, this carbon has 1 electron. Here it is cation, so it is empty. What is the energy of this electron present in 2pz orbital of carbon?
Alpha.
Alpha. This is alpha. Here I don't have electron, so you need not put alpha. So alpha plus alpha is 2 alpha. You subtract 2 alpha from this. Okay. So pi electronic energy is 2 alpha plus 2 root 2 beta minus 2 alpha. If I subtract, I will get 2 root 2 beta. Yes, this is the pi bonding energy of allyl cation. Take note. The second system is allyl radical. So allyl radical, yes, it has 3 molecular orbitals. This is psi1, this is psi2 and this is psi3. Energies of these molecular orbitals are E1, E2, E3. Okay, E1 value is alpha plus root 2 into beta. This is just alpha. This is alpha minus root 2 into beta. Now, anyone tell me how many pi electrons are there? Number of pi electrons.
3.
This pi bond has 2 electrons, and here we have a radical electron. This is also participate in resonance, correct? Therefore, there are 3 pi electrons. So this electron should be considered as pi electron because it involves in resonance. So there are 3 pi electrons available. Okay, so and each molecular orbital can accommodate only 2. So place 2 here and place 1 here. This is the electronic arrangement, ground state configuration of allyl radical. Now, what is the pi electronic energy? I have 2 electrons here, so 2 into E1 plus we have 1 electron here, so 1 into E2. So 2 into E1 value is alpha plus root 2 into beta plus 1 into E2 value is just alpha. So what we get is 2 alpha plus alpha. I will get 3 alpha plus 2 root 2 beta. This is the pi electronic energy of allyl radical. Now, what is the pi bonding energy? Pi bonding energy equal to pi electronic energy. Okay, this is allyl radical, no, so I will put a dot. Yeah. So within bracket I will put a dot. It indicates allyl radical. So pi electronic energy of allyl radical minus before bonding. What is the energy?
3 alpha, sir.
Yes, very good.
Wow.
Each carbon atom has 2 pz orbital and each one has 1 electron now, correct? So this is alpha, this alpha, this alpha. So you have to subtract 3 alpha here. Therefore, 3 alpha 3 alpha cancel, you will get 2 root 2 beta. Pi bonding energy of allyl radical is 2 beta. Take 2 root 2 beta. So, we move on to allyl anion. In the case of allyl anion, we have 2 electrons. This 2 pz orbital has 2 electrons. So, the electronic configuration is, we have 3 molecular orbitals, psi 1, psi 2, psi 3. These are the wave functions of the molecular orbitals. And what is the corresponding energy? The energies of the molecular orbitals are E1, E2 and E3. Now how many pi electrons are there?
4, sir.
There are 4 pi electrons. So place 2 here and 2 here. Energy of this orbital is alpha plus root 2 into beta. This is alpha minus root 2 into beta. So what is the pi electronic energy? Anyone? Tell me the value directly. Multiply this by 2.
4 alpha.
2 very good. 4 alpha plus
beta.
2 root 2 beta. Yes, tell me what is the pi bonding energy directly.
Alpha plus 2 root 2 beta, sir.
Why alpha? It should be 2 root 2 beta. Because, listen, here the 2pz orbital has 2 electrons, right? For each electron the energy is alpha, correct?
Okay, sir. Okay, sir.
So, for both electron, the energy is alpha plus alpha. You will get 2 alpha here and here 1 alpha, here 1 alpha. If you subtract 4 alpha, you will get this answer. Okay?